lecture series on real analysis. In this lecture, we are going to see some examples of compact sets on R2. Here, we consider the set R2 under standard Euclidean metric, and few of the subsets of R2 are given to us. We need to examine for the compactness. Here, the idea that we are going to make use to verify the compactness is the Heine-Borel theorem. That is, in Euclidean space, a set is compact if and only if it is closed and bounded. That is the idea that we are going to make use here. Here, let me try to explain these things with the help of a diagram to check whether the given set is closed and bounded or not, right? So that will help you in a better way to understand. Okay, let me choose this to be of something of this form. Okay, here in the first, what is given? It is given that R2 minus I cross I. What is this I cross I? It is the collection of entries, collection of order tuples where these entries are taken from I. What is I here? Here I denotes the set of integers. So you will have points of this form on this axis. Okay. Similarly, you are going to have parallel points. It is going upwards as well as downwards. You will have parallel points, and it is going to cover the entire. This way, you can collect the points. It is going till infinity on both the sides and on the upper and lower sides as well. Which means, what can we say? If you are going to take a plain sheet of paper, have dots of this form, equally distant dots. Okay, it has to be filled with the entire paper. Now you can see the paper with the dots, right? So those are the points of I cross I. You have to remove those points from your R2. That is what here they have meant, which means in the entire sheet of paper you have removed the dots that you have. Okay, after that you have to check for the closedness and boundedness. Here, if any one of the condition fails, then we can very well say that that set is not going to be compact set. In that case, it is going till infinity. We have removed only a countable number of points, but the set still remains unbounded. So the first set cannot be a compact one. Therefore, it is not compact, right? So in the second one, here also they have given that we have to remove this part from R2. Okay, what is that part? They have given 1 less than x square plus y square less than or equals 8, right? So what? Let me take this part alone. So it is x square plus y square greater than 1, and when I take this part, I will have x square plus y square less than or equals 8. What is this x square plus y square? It denotes that it is going to be a circle of some radius with center at origin. Okay, so here greater than or equals 1, which means if you are considering it to be in the form of x square plus y square equals 1, it is going to be a circle of radius 1. So you are going to get some circle of this sort. When you have x square plus y square less than or equals 8, you will have some big circle of this form. Okay, I am not very accurate with the measurement, but somehow this is what I am going to get. Here, greater than 1 means it has to cover the points above this circle. Okay, so it is going to cover the points above this circle. Here we have less than or equals 8, which means it is going to cover the points below the circle. The intersection of these two will be what? This is going to be this region. Okay, whether we are including the boundary or not, it is a question mark now, right? So here you can see that in this we have included the boundary, which means the big circle, the boundary of the big circle is included in my set, whereas the boundary of the small circle is excluded from my set, right? So this is the set that is given here. right? Then here what should we do? We have to remove this part from entire R2. So when we try to remove that part, we will have this region and the region outside the circle. So this is my set now. Now I have to check whether this is closed and bounded or not. Here you may see that this is not going to be bounded because I have removed this part. A certain part I have removed and I am checking for the other parts, which means it is not bounded. That is why we can very well conclude that the second set is also not compact. Okay. So the idea that we have used to verify this is compact or not, the same idea can be implemented for the sets 8 and 9. Here let us see what is happening. The same thing, right? So here we are not talking about the green part, we are going to restrict ourselves to the black ones, right? Here you see you have included the boundary of this circle, whereas you are not including the boundary of this circle. So this set is, if you are considering only the black part, you can very well come to a conclusion that this is going to be bounded because all the entries, all the points inside the circle will satisfy this condition, that is x square plus y square less than or equals 8. It is going to satisfy that condition. Okay. Now we have to check whether this is closed or not. Okay. If you are going to take a point on this boundary, okay, a very small neighborhood of this point will cover some points of the set, which means all the points on this boundary will be the limit points of this set, but the points on the boundary are not included in this set, hence the set cannot be a closed one. So when the set cannot be a closed one, it cannot be compact, right? Here you may see that both the boundaries are included, therefore it is a compact set, right? So now let us move on to the other examples. In the third example, what is given? They have given some equation, that is x square upon 15 plus y square upon 16 less than or equals 17, and in the fourth one it is greater than or equals 17. Here you may notice something, that when you like what, this is an equation of what? This is an equation of an ellipse, right? So you are going to have some ellipse of this sort. Okay, I am not very well accurate to the diagram, but you will have some ellipse which on distance looks like a circle because the entries are so. Okay, this is you are going to have some ellipse of this sort. In the first, we are considering the interior of an ellipse. Okay, whereas in the fourth one, we are considering the exterior of this ellipse. In both the cases, boundaries are included. That is, I am talking about the boundary of this ellipse. Okay, the boundary is included in both the cases. In which case, the set is going to be bounded and closed. You may notice that the boundaries are included in both the things. Therefore, under both cases, you will have the set to be closed. Whereas in the first case, that is this case only, the set is going to be bounded. Therefore, this set will be compact and this set is not compact. Okay, here both the sets satisfy the condition of being closed, whereas the first set alone satisfies the boundedness. The second set fails to satisfy the boundedness. Okay, now let us see about 5th and 6th. Here you may, in this also you may notice that the 5th and 6th are complement of one another, right? Here what is happening? You have, so this is, if you consider this to be equal, you are going to have some hyperbola, right? So you will have a hyperbola of this set, okay, and it is going till infinity on both the ends. Now the first is going to cover the points of this set, and the second is going to cover the points of this set. Okay, which among is going to be closed and bounded? Okay, that we have to see. Here, since the boundaries of this hyperbolas are included in both the sets will satisfy the condition to be closed. Now we will have to look for the boundedness. Okay, here by looking at a diagram, you may think that both the sets are unbounded, because in both the sets it is going till infinity, right? So with it, can we come to a conclusion that both the sets are unbounded? No. Here, if you see, this is going to satisfy this condition, right? So all the points in this are satisfying some condition of this set. Whatever may be the value of x and y that you take, it is on evaluation to this, it will give you some bound. So this set is going to be compact since it is bounded. Okay, it may look unbounded, but actually it is bounded one. You may check with the help of this one. Okay, and this is not compact since it is unbounded. Okay, and we have one more example, that is x square. Okay, so here what is the value of x that I can take? I can take any x, right? So in this axis I may take any value. What is going to be x square? It is going to cover all the points in the upper region. So this is going to be my collection of the sets, right? So here it is bounded below, but the above bound we do not have, and even in both the cases it is going to infinity. When you check for it, it will turn to be a closed set, but it is not bounded. So it is also not compact, right? So in this example, hope you might have had some idea of compact sets and examples of compact sets in R2. If you have any queries in this lecture, you may post it in the comment section. That will be clarified within 24 hours of time. Thank you for watching.